According to general relativity, there are regions of space-time in space whose gravitational pull is so great that even objects moving at the speed of light, including light quanta, cannot leave them. These regions, called black holes, actually become such powerful gravitational formations that no one and nothing, once inside them, can get out and cease to exist in our universe. Recently, the problem of black holes has attracted considerable interest, although the idea itself is not new and was put forward about 200 years ago by the English astronomer John Michell in 1784. He proved that if the mass of a star is large enough, then light will not be able to leave it, and it will be invisible to observers. It was only an assumption, but when black holes were actually discovered and their existence was fully confirmed, the news shook the entire scientific community. Each scientist had his or her own point of view, but the most interesting was expressed by the theoretical physicist Kip Thorne, who wrote that among all the inventions of the human mind, from unicorns and chimeras to the hydrogen bomb, the most fantastic is the idea of a black hole, a region of space separated from the rest of the world by an unbreakable boundary that nothing can overcome. A black hole has such a strong gravitational field that even light escaping from it is captured in its deadly grip, and time is slowed down. Although the idea of black holes seems more suited to science fiction novels or myths than to the real universe, the laws of modern physics actually require their existence. In order to understand how a black hole appears, we first need to recall the life cycle of stars. So, the life of a star begins in huge molecular clouds, where a protostar is formed. This process involves cold clouds of interstellar gas that are compressed by gravity. At this stage, the gas globe cannot yet be given the status of a star, since the temperature in the center is not yet sufficient to start thermonuclear reactions. The gas pressure inside the ball is not enough to balance the gravitational forces, so the compression continues. This compression is uneven, and after a certain time, a hydrostatically balanced core is formed in the center, which can be considered a protostar. Further compression leads to a decrease in the size and increase in the density of the core. This process continues until the center of the core reaches a temperature sufficient to start thermonuclear reactions of helium fusion from hydrogen. The compression process also forms protoplanetary disks around the star, which can later develop into planetary systems. This is the first stage, namely birth, for most stars in the universe. However, the further life of different stars can differ significantly from each other. The main factors are their mass and composition, which directly affect the overall lifespan of the star and what it will turn into after its collapse. It should also be said that the life of a star does not always run smoothly. Its evolution is complicated by its rotation. Sometimes it can be very fast, up to the limit of its stability. Consequently, red dwarfs of spectral class M, which have a mass of only 10% of the mass of our Sun, will live a very long life. It can be up to 100 billion years. At the same time, stars of the spectral class G, to which our Sun belongs because of its greater mass, have a shorter lifespan. It is on average 10 billion years. The greater the mass of a star, the shorter its lifespan. This is because stellar fusion fuel is not infinite. Therefore, the lifespan of the largest stars in the universe can be several million years. Mass also affects the final outcome of a star's life. For example, when our Sun dies, it turns into a white dwarf. The process of this transformation begins when the star can no longer maintain the proper level of fusion, and all the hydrogen in its center burns out. As a result, the core of the star shrinks, and its outer layers expand. After a while, the star turns into a red giant, in which more and more helium is formed. If the initial mass of the white dwarf does not allow the core temperature to rise for further reactions, then eventually the outer layers of the star become a planetary nebula. The core of the star, consisting mainly of carbon and oxygen, remains in the form of an incredibly dense and compact object, called a white dwarf. Thus, after the death of a star, the following objects can form. The first is white dwarfs. The second is neutron stars, whose mass is limited by the Oppenheimer-Volkow limit. If the mass of a neutron star is less than this value, the pressure of the degenerate neutron gas can compensate for the forces of gravity. The third is the formation of a black hole, which is the result of the evolution of a massive star. When a huge, heavy star exhausts its main supply of fusion fuel to maintain its equilibrium, it has to maintain its fusion based on heavy elements for a certain period of time. During this time, irreversible processes of hydrogen transformation into helium and then into carbon and so on up to iron take place in its interior. Eventually, the collapse becomes inevitable and the star's core begins to shrink rapidly. In less than 1,000th of a second, the star turns into a black hole. Shortly after the start of the compression, a very powerful burst of X-ray and gamma-ray radiation occurs. The collapse continues, and it becomes increasingly difficult for photons to resist the increasing gravity. The photons that now leave the surface of the star move at an angle and have a curved trajectory. The same photons that moved parallel to the star's surface remain in its orbit. After passing the event horizon, the star becomes invisible, leaving behind only deepening darkness. Having completed its evolutionary life and reached the end, the star leaves an incurable mark in the form of a black hole. But these are only high-mass black holes, and there are also medium-mass black holes in the universe. Who are these objects and how do they arise? A medium-mass black hole is an object with a mass that is significantly greater than that of a stellar mass black hole, but significantly less than that of a supermassive black hole. These objects, known as medium black holes, are probably less common in the universe compared to ordinary stellar mass black holes and supermassive black holes, as the mechanism of their formation is not fully understood. There are several scenarios for the formation of medium-mass black holes. The first scenario involves the merger of stellar mass black holes and other objects through accretion. The second scenario involves the collision of massive stars in star clusters and the subsequent collapse resulting from such collisions. The third scenario involves the formation of these objects at an early stage of the life of the universe, shortly after the Big Bang, and the fourth scenario involves their formation in the cores of quasi-stars at the early stages of the life of the universe. Even if the process of forming this type of black hole has not yet been fully revealed, astronomers have already begun to detect these objects in the vast expanses of our universe. For example, in 2019, scientists from the National Astronomical Observatory of Japan discovered a Jupiter-sized black hole in the Milky Way galactic center, with a mass about 32,000 times that of our Sun. Although the most likely scenario for the formation of medium-mass black holes is the merger of two small black holes, the chances that they will collide in the vast expanse of the galaxy and begin to spin in a gravitational dance with a fairly predictable ending are still very small. All in all, these discoveries suggest that black holes are much more common in the universe than we previously realized. But there are real giants in this vast expanse of space, especially in terms of mass, which is simply mind-boggling. According to scientific concepts, there are four main scenarios that explain the emergence of black holes. The first of them, as already mentioned, is a gravitational collapse or a sudden compression of a sufficiently massive star at the final stage of its life. The second scenario involves the collapse of the central part of the galaxy, or even just galactic gas, since black holes are usually located in the center of almost all spiral and elliptical galaxies. The third scenario involves the formation of black holes immediately after the Big Bang, when fluctuations in the gravitational field or matter occur. Such black holes are also known as primordial black holes. The fourth scenario describes the emergence of black holes as a result of high-energy nuclear reactions known as quantum black holes. But how did such monsters as supermassive black holes, whose masses can reach several billion solar masses, form? The difficulty in their formation is that it requires a large amount of matter to be concentrated in a relatively small volume. In addition, the matter must have a very small initial angular momentum, i.e., rotate slowly. Usually, the speed at which matter falls into a black hole is limited by the angular momentum, which limits the rate of increase in its mass. There are several hypotheses that have tried to explain the process of their formation. The most obvious of these is the hypothesis that supermassive black holes did not become so massive at once, but gradually by absorbing other smaller black holes and objects in the universe. Another hypothesis suggests that supermassive black holes can form during the collapse of very large gas clouds, which then turn into stars with a mass of several 100,000 suns or more. However, such stars quickly become unstable, leading to radial disturbances and their collapse into black holes. This process goes past the stage of a new star, where the explosion would have scattered most of its mass, preventing the formation of supermassive black holes. When it comes to their enormous mass, this is no longer an exaggeration. We already have confirmation of the existence of one of the oldest and largest supermassive black holes in the universe, called TON 618. The distance to TON 618 is a very large distance of 10.4 billion light-years. TON 618 is a very bright, radio-loud quasar located near the North Pole of the constellation of the Hounds. This space object is probably one of the most massive black holes ever observed. Its mass is estimated at about 66 billion solar masses. Supermassive black holes such as TON 618, which are millions or billions of times more massive than our Sun, usually increase their mass rapidly by absorbing material from the surrounding disk. This leads to a huge emission of radiation in a very limited area around the black hole, and scientists call this phenomenon a very bright compact source. The enormous black hole, TON 618, is part of a quasar and thus an active galaxy. This black hole is currently forming thanks to superpowerful radiation, which then alerts the entire galaxy where TON 618 is located. Unfortunately, we cannot observe it directly because its light is obscured by the light of the quasar. The quasar of the black hole, TON 618, is so bright that it emits a volume of light equivalent to that emitted by 143 million suns combined. When this enormous black hole absorbs a lot of matter from its surroundings, it heats up considerably, emitting huge amounts of powerful radiation. Only the most powerful explosions are thought to be able to darken quasars. However, after such explosions, the brightness usually lasts only a few weeks, while quasars can shine for millions of years. Although TON 618 is considered the largest black hole, it may have competitors, other objects that are heavier and larger than it. Some of them, according to theories, may have been formed by the compression of large clumps of dark matter in the early epoch of the universe. These potential black holes can be of incredible size and mass. Some scientists view the formation of black holes as a small-scale model of what general relativity predicts could happen to our universe. In general, it is generally accepted that we live in an ever-expanding universe, and one of the most important questions in science is what the nature, past, and future of the universe is. Current observational results indicate that the universe continues to expand. But one of the most interesting questions is whether this process will slow down over time, or perhaps even stop, and then begin the reverse process of contraction, which will bring the universe back to the state of singularity from which it all began. Perhaps one day we will be able to figure out how the universe will evolve. But it may happen much faster than we think. So the only thing left is to study the limited data we have available at the time of the birth of black holes. By studying the physical laws that govern their lives, we can come at least a little closer to answering the question of the fate of our universe. Thank you for watching, dear friends. Your kind words and support motivate me to make more and more interesting videos. Don't forget to subscribe to our channel because we have many more interesting and exciting things to share with you. See you on our space journey.